Good afternoon, everyone. We're just trying to re-establish connection here in Dubai. Yahya will rejoin us shortly. So thanks very much for your patience.
Yeah. Hello. Hello.
You're back. You're back.
Okay. So that was a disaster, huh?
It was just a mishap. Disaster is a big word.
But the building is still standing. So I think that's the good news. So my apologies to everyone for that. Yeah. So, but we are probably also running out of time. Yeah. Do you want me to speak for another 10 minutes and just present what you missed and then open it up for discussion? How would you like to do it?
Yes, it is okay, Mr. Yahya.
I think time is not a problem, and maybe we could also discuss a little bit about the structural system and how that was, because I think a lot of people will be interested to see how the existing foundations piles were then integrated into the new system and how the structural system basically, because we have lots of audience in engineering, obviously, and they are setting up messages on the board. They're very keen to learn a little bit about the overall scheme of the structure as well. So maybe, I mean, it's up to you, but I think that will be of a lot of interest to us. Yeah.
Okay, sure. So Chris, at what point, Chris, did I?
We lost you on some of the model photographs, the physical model photographs, close-up models. It was about 7 or 8 minutes ago. So.
Okay, so I'll try and pick up where we left off. Yeah.
Yeah.
Can you see something on the screen?
Yes,
now?
we can. You're scrolling back.
So, did you see the video of the?
No, we didn't see the video. And maybe the video that froze it. Who knows? I think if you keep going back, we didn't see any of this.
Oh my God!
Stop! Yeah, we were here. We were in the we were just looking at the model photographs. Yeah, I think start there. That's a good place to start.
Okay, so these are the. Did you see these construction photographs?
No, we didn't. This is a good place to start, I think.
Okay, so these photographs were taken 2 weeks ago, during the first raft pour, and you can see the amount of steel there. You can also see the rectangular shape of the original core, and then you can see the pile heads. And also you can obviously see the bracing to stabilize the foundation walls. Yeah, Chris, am I still there or am I disconnected?
You are still here. You're in play. Yeah.
And Dr. Naveed, the presentation today is really multidisciplinary. It's to give us a feel not just of the structure, but also of the complexity of designing a project such as this, and using, in this case, parametric methods to design and optimize the skin of the tower, because the tower is not a regular shape. It's changing in geometry as it goes up, and the floor plates change. The floor plates vary from floor plate type 1 all the way up to type 6 on the drawing. And so really the challenge then is how do we, in this case, one of the challenges is how do we optimize and design an envelope, in this case, that allows us to produce a glass tower, realize a glass tower, but purely through cold bending, so that the glass panels themselves are flat, but when they are brought to site, the panels are then pushed physically and one corner is bent back to create a warped surface. And cold bending has very defined limits as to how much you can do that, and those limits that are then computationally calculated, and we then create an optimized scheme which has a high level of repetition for economy, but also maintains the design intent of a tapered building. And using computational methods, in this case 3D modeling in Revit of the tower, was super important, because no two floor plates are the same. Every floor plate in this building is unique and different. And we use computational methods to generate the shape, and then Revit modeling to produce the drawings, so that the drawings are a byproduct of the modeling. So I think Chris, have you seen any, has the team seen any of these views of the building?
No, I don't think so. This is, yeah,
this is all new, yeah?
Yeah.
And Chris, am I still there, or have am I still online?
You're still there. You're still online. You're still online.
That's good news. Yeah.
Thank you.
So there you have it. It's still early days. We have a 3-year construction program for the project. It's a glass-clad project. These are some early renders that show you where we are heading. An observation deck at the very top of the tower with a infinity edge horizon pool, we call it, a second pool at level 78. And are thinking about the construction sequence then. A slip-formed in-situ concrete core, outrigger floors, steel structure at the very top, and then the floor slabs, and you can see the atrium gardens. There's 12 of them. And then, of course, the challenge of how to wrap the skin on the project. Yeah? And this process of going from a relatively simple rectangular building to a much more complex project is not always linear. The process itself has a life of its own, and really, as designers then, we are always looking to see how we can respond to existing conditions. In this case, the fact that the piles existed in the earth, they were designed for a tower with 2 rectangular cores and a raft. And our scheme, of course, is different. The scheme is for a oval-shaped core, an oval-shaped tower, basically sitting in the same location as the original scheme. But because of this specificity and the fact that the building is about 100 meters taller than the originally designed building, we discovered very soon that we would need to sleeve in and embed within the piles an additional 21 piles. And these vary in dia from 1 meter in dia to 1.5, length from 30 meters to 48 meters in length. And then to cap it and with a deep raft that will distribute the loading of the tower, of the newly shaped tower. onto the foundation. And our engineers can talk more about this than I can. And I'm hoping Danilo, if he's there, and Tuk, I'm hoping they can answer some of your more specific questions on how we dealt with this. But we took it on. We understood that our decisions related to the tower would have challenges for us in terms of what's already there. And we dealt with that, I would say, with determination and with a very fine sense of how to solve the problem. Chris, in case I get disconnected, will you call me on my mobile? I think that would be the best way forward.
I will do. Yeah, okay. You're still going.
So wind, there's a very strong and predominant sea breeze that arrives at the site from the northwest. And in our early studies, we took on some very rudimentary computational fluid dynamic studies where we tested various shapes for the project. At that time, we thought the building would be about 340 meters. It's changed a bit now, it's about 365. But the early rough analysis comparing the originally shaped rectangular tower, which you see on the left, the rectangular tower, to the more tapered oval shaped tower. And as you would expect, we found that a rectangular tower facing the incoming breeze created tremendous vortex shedding on the leeward side. And with that, obviously, the need for more structure to stabilize the building from its own dynamic oscillations as a result of the vortex shedding. And then we tested different shapes, square, a rotated square, eventually an oval, and then a oval that's a shape that is actually tapering. And you can see that there's a dramatic change in the vortex shedding profile as we moved away from a rectangular shape to this more fluid shape. And the initial data, early data, showed that in terms of forces and moment, there could be a 40% reduction as we optimized the shape of the building, as we moved away from a rectangular to this oval shaped building from the base case. We then worked with RWDI for extensive wind tunnel testing of the project. This is the wind tunnel in India, and their analysis again reinforced and corroborated our earlier analysis in terms of the efficiencies that come from the shaping of this building. The project is obviously modeled three-dimensionally in Revit, and we model all disciplines: architecture, structure, mechanical, electrical systems, and even interior design is all modeled three-dimensionally, because that integration of the different disciplines becomes a key to producing a set of documents and to producing a design that actually works. And then the idea of these gardens, these naturally ventilated landscape spaces that are stacked vertically on the ocean-facing side of the project. And that's been a very exciting exploration for us, because these spaces are not air-conditioned, they are comfort-cooled for only where people are in their comfort cooling zone. And by doing that, we have been able to achieve fantastic savings in terms of the cooling load on the project. And our energy consumption on this project is significantly below the Dubai mandated energy code. And we've been able to do this because early on, we recognized that these gardens themselves should be such that we cool where we need to, and we allow for a temperature gradient, a vertical temperature gradient through the space, which could be as much as 14, 15 degrees in March, And then in the height of summer, you can see that the temperature gradient is even more. It's about 17 degrees between the 24 degrees where people are to the very top. And by designing the project to allow for this, i.e. by having the insulated thermal enclosure set into the building rather than on the face. The face of this atrium is uninsulated glass, whereas the insulated envelope is behind the atrium. That has allowed us to propose these really exciting shared spaces, but without huge operational costs related to maintaining them and cooling them in this environment, very harsh summer environment. I'm just going to scroll very quickly through the plans. You can see the shaping of the building. It's a symmetric structure with a central core and radial shear walls. And then of course the slab edge changes as the shape of the building changes. And the shear walls themselves are translating a bit along the axis as the shape of the building and the geometry adjusts. And this is the very top of the tower with the observation deck. The elevatory is, I think I've lost the PowerPoint again, Chris, for some reason. Yeah? Chris,
yeah,
are you there?
It's coming back. Yeah, you're just refinding it again.
For some reason, the PowerPoint is tripping. I'm not sure why. But, let me try and get back, and then let's open it up for a Q&A.
You've gone past. You've gone past.
So we were looking at the elevatoring strategy. There are 20 elevators in this project, from elevators within the podium to low-rise and high-rise. And we've spent a lot of time looking at that aspect. I think I lost the PowerPoint again. Yeah.
Yeah.
Let's just wait for it to catch up. No, it's tripping. Yeah. So why don't we open it up for discussion, if that's okay? Yeah. So I apologize for the technology. This seems to be an issue. Chris, are you there?
I'm here. Yeah.
Okay.
So, Mr. Yahya, so do you want to, if you want to start that discussion with Dr. Naveed and Mr. Engineer Hosi. So let me introduce Engineer Hosi C. Mr. C is CEO and President of C Square and Associates, C Square Plus Associates from Philippines, which is a structural consulting firm, which he has done several tall building projects in Metro Manila and in other cities of the Philippines.
Yes.
So let me start with Dr. Naveed for his opinions and questions on structural design of a steel tower.
Great,
Yes,
great. Thank you so much.
Yes. First of all, I would say, thank you so much. Really, it was amazing how the project has shaped, and to be able to see the project process through the eye of the designers and the architects is always very, very. It unfolds a lot of things that we never get to see in the final product, and to be able to be part of that process is a privilege and an honor. I think I personally enjoyed it very much. And thank you so much for sharing this with us, right from the beginning, especially a project of this kind, where the original design was already done in a different form, and then with the foundations there. It's amazing that normally if somebody comes to us and say that we have a building, and would you mind adding 100 floors onto it or 100 meters to it? I don't think people will take that seriously. They think, well, what are you talking about? The foundation is already done. Maybe we can add a few meters, but not 100 meters. So it's really amazing challenge that your team has undertaken, and especially how it transformed the form from a rectangular to such a beautiful architecturally, as well as you shown, the engineering point of view, the wind balancing of the shape and everything. So I think it's a fantastic project for us to be a witness of. So I think the main objective of our talk has already been achieved, because you have very clearly demonstrated how the project concept develops and how different disciplines come together to create a masterpiece like this. And it clearly also shows that the structural issues or structural challenges were a major part of that. I'm just, I think for the benefit of our participants, I think if your team or yourself could elaborate a little bit on how the structural system itself was developed in terms of the interaction between the core and the outer shear walls, and how the location of the outrigger floors were decided, because that's always an issue for engineers, and to see whether it fits with the architect's vision of these outrigger floors which have to be there. So if you could say something about the outrigger floors and how they were selected and how they were positioned and how they sort of accommodated the structure as well as other needs.
Okay, so I'm not sure if Danilo is on the call. Danilo, are you on the call by any chance?
Actually, yeah, Mr. Danilo, I think I didn't see his name, but Buituk is here.
I think Tuk is here. So Tuk, I'm running. Can you see the video that shows the structural concept and then the outrigger flows? Can you guys see this video?
Yes, we can see that. Yeah, we can see that. We can see that.
Okay, great. So Tuk, could you talk a bit about how we evolved the structure and the one third locations for the outrigger walls? Can you just talk a bit about that?
Yeah. So my name is Thuk. I'm the structural engineer for the project, and we've been our structural engineers have been working very closely with Yahya, shaping the tower. So when we look into the existing design of the building, I mean the existing piles, we knew that in order to make to do a 365-meter tall tower, we really need to optimize both the gravity loads and the lateral loads. So for the gravity load, we're looking into reducing the partition loss, optimizing the slab thickness in order to reduce the reaction at the base. We knew that we wouldn't be able to do much about the thickness of the core walls or also the shear wall. To reduce the lateral load acting on the building, we look into working with the architect, shaping the tower to making it very aerodynamic in order to reduce the wind load. For seismic, besides reducing the gravity load, which directly affect the amount of seismic force acting on the base, we also conduct a site-specific study to determine the level of seismicity at the location of the tower. We work with architects and vertical transportation engineers to shape up the core. It's one of the very important element of the structure. We work with the interior design, layering the radial shear walls at the perimeter, and along the height of the tower, we have provided 3 outriggers with perimeter reinforced concrete bell walls, very well integrated with the MEP systems. So if I have to say a sentence about the structural system for this building, it is the building wall system enhanced with 3 levels of reinforced concrete outriggers and bell walls. Yeah.
Yeah, thank you
Thanks,
so much.
Yahya.
Yeah, thank you so much, Mr. Yahya. And let me just, it's really an honor for us that Engineer Buitak, the designer of this building, is also, with AIT and taking our professional master's program in tall buildings. So we are really honored that designers of this caliber are collaborating with us. Maybe I think I will pass the floor to Boise.
Yeah, thank you so much, Dr. Navid. Thank you so much also for the great presentations. So it's always, a dream of a structural engineer to design a building, such, a height, 300, more than 360 meters. In the Philippines, you're only designing 270. So I was amazed, just because of, shaping now the tower, configurations. You were able to, correct me if I'm wrong, you were able to, delete the need of any dampers, right? Am I right in saying that? There's no dampers, only outrigger.
Yeah. There are no dampers. There's no
dampers, right?
There's no TMB requirement. Yeah.
No dampers. No dampers.
Yeah. Just the core alone plus the radial shear walls, and you're able to shape now the perimeter, the shape of the tower, and you're able now to address now the the wind loads, right? And that's the reason why you're saying that you don't need any dampers, simply because of this technique that you actually did, which is actually quite amazing.
Yeah.
Thank you so much.
I just want to add a note here. When we look into the wind design, basically, we knew that our designer, our architects, wanted to have an observation platform on the very top of the tower. So we've been working with the designer to open up the crown of the tower in order to reduce, I think, quite significantly the amount of wind load for the top part of the tower. And that's it has resulted in an elegant design, but also efficient structural system for the crown.
Yeah, thank you.
If I may, once again, Mr. Yahya, I think, Mr. Yahya, I must say that, the way that you have presented and developed this project is really very instructional to a lot of us working in this field, and especially your focus on collaboration and also on focus on getting the final solution through all these steps has been really amazing. And I think this is the main learning experience for all the participants, I can say on behalf of everyone here, that we have actually witnessed today. One of the most of us engineers normally attend the conferences conducted by other engineers and presentation from other engineers, and we rarely get to see how the project actually is developed from architectural and a more integrated manner as you presented. So I think this has been really very amazing experience for me personally, and also for the participants. I think maybe we can go ahead and open it for the questions. What do you think?
Yes, sir. So let's continue for a Q&A session from audience. If you have any question, please type in the chat box.
So I think some of the questions in the chat box have already been answered, because there were some questions about structural system. So I think they have already been answered. So if there's any other question from anyone, please do type in.
Yeah, Dr. Navid, I have seen a question over here. It's from I think Mizano Rahman. He's asking, is there any rational reason for not to choose a composite structural system instead of reinforced concrete? So I'd like to answer this question by saying that usually for a super tall building, sometimes composite steel and concrete structure have been used in order to reduce the thickness of the cover, or reduce the cross section of columns. It's all about the feasibility, the study that we have done for the market in Dubai. We knew that in Dubai, if we do the tower fully in reinforced concrete, we'll be able to reduce the construction cost by around 20%. So when we look into the reinforced concrete structure, we've been using very high concrete strength along the and the strength of concrete is actually varying around the height of the tower. At the base, we have we have been using concrete C85. It means the F'(C) would be around 70 MPa, and then the F'(C) being reduced to 60 and 50 when we get to the very top part of the tower. Yeah.
Thank you so much. I think there is one more question.
There is one question, yes.
Yeah,
yes. The question is regarding the warped surface on the glass facade. Was it the outcome of the wind simulation via flow design wind tunnel requirement, or is it an theoretical outcome?
I think you can answer this. Yes.
I think maybe the question is what determined the shaping of the building, right? Because the warping of the glass was a result of the original idea of having a building that is shaped this way, tapered, we call it. And the tapering, the varying geometry of the flow plate is a direct result of our initial CFD and wind analysis. They call it confusing the wind. I guess some people say that, right? You confuse the wind by not presenting a regular geometry all the way up the tower. The geometry changes. And that has a very significant effect on vortex shedding and the lateral oscillation of the tower. So we realized early on that we didn't want it to be a simple extruded shape. We wanted the shape to be tapered and changing, although subtle changes because of the program. The hotel program only allowed us to do so much in terms of shaping. And once we had a shape that we felt worked with the program and also looked good, we also then tested it against the glass manufacturers' parameters related to cold bending of glass. And so it was a back and forth. It was an iterative process of going back and forth. And we found a solution that worked. I'm not sure. Does that answer the question?
Yeah, I think exactly. I think that was the question. And if I may say, if I may continue with the question, as an architect or as a designer, when you started the project, did this shape was the one that you intended to achieve, or like you said, it was the result of some iteration? So what was the starting shape where we started with?
We started with a simple extruded shape. And it was in, when I showed Dr. Naveed, I showed some of the models. The earlier models did not have this taper.
I see.
It was a relatively simple shape, and there was a lot of debate within our group whether to taper or not. Because by creating a tapered shape, we actually ended up generating a huge amount of computational work because all the flow plates are different in the tower. But we elected to go for it, and we tested it against wind analysis. It has of course, a marginal positive impact. The main impact on wind really had to do with moving away from the rectangular shape to this curved shape. That had the biggest positive impact in savings in terms of vortices and loading.
Yeah. If I may ask this question, after that, I think we'll go back to some of the questions from the participants. Because by choosing this complex shape and this geometry, you actually increased a lot of your own effort, design effort, and the design time. So was the client agreeable to this additional work or additional effort and time required for this shape to be implemented?
Yes, our client was very receptive to this, and the project was tendered early. It was tendered really at the end of design development. So during the tender and award process, we continued to work on the project, to work it out. And I would say it's been one of the most complex projects for our group over the last at least 25 years, 24 years that I've been with this group. I would say this project really tested our own tolerance for pain. I think that would be the word, yeah. And it's good. It's good to test your own limits. And perhaps by testing it, you will embrace new technologies and new ways of doing things. So yeah,
exactly. That was the kind of answer I was sort of hoping to get. Thank you so much. I think we'll go back to the questions now.
Yes. Next question is, can you tell us more about the foundation of this structure? And more elaboration regarding how you were able to add 100 meters more to the existing foundation.
Yeah, thank you. I'd like to answer this question. So the question is, tell us more about the foundation of this structure. But before speaking about the foundation, I would like to, to let all of you know that when we do the when we work with the architect for this for the design of this tower, at the very beginning we requested them to consider the use of drywall systems instead of any kind of masonry work, block work. They all will be much more heavier than a drywall system. So all the partitions on the typical floors are made of drywall. We are able to bring the supported load significantly less than a conventional design in any building in Dubai. The second item that we were optimizing is that the floor plate itself. So we look into various options for the floor plate. We look into optimize. We work with the best post-tension designer in Dubai to arrive with a very thin flat plate for the typical floors. Besides that, we were also looking into some kind of voided slab systems using, Kobiak's plastic former. We compare different systems, and finally we have adopted the post-tension slab for the typical floors in the tower. By making the tower aerodynamic, we are able to reduce, as you have seen in some of the charts that Yahya presented, we were able to reduce the amount of wind load in the tower by almost 40%. All of the factors that affect the tower foundation. So even though that we have a lot of existing piles on the site and they have a very high capacity of around 30. Each pile has a compression capacity of around 37,000 kilonewton. However, since our tower core is not exactly happening in the location of the previous cores, we were facing some issues. Some of the pile is slightly overloaded, and we have to put in additional 22 bore piles with the same length, same diameters. In terms of foundation design, we work with a specialist geotechnical engineer in New York. The company name is Langan International. We've been doing a lot of iterations, the iteration between geotechnical engineer and structural engineer in order to arrive with the precise and efficient spring stiffness for each of the individual piles. So in this tower, we have total 175 piles. The piles are 1.5 meter diameter, 50 meter deep under the tower. And under the podium, piles are 1 meter in diameter, and the depth is around 30 meters. Yeah.
Thank you. Thank you so much. Next question.
Next question is, which loading is governing the design, wind or earthquake?
Yeah. Okay. Thank you. So in Dubai, Dubai is the seismic level in Dubai is very mild. It's it's a moderate, it's even lower than the moderate seismic zone. So for this tower, wind is the governing lateral load.
Okay, thank you. And next question is, was PVD considered in the design?
Okay. So we were thinking about doing a performance-based design for the tower, and we actually have been discussing this with Yahya at the beginning of the design. As you know, that in Dubai and the UAE, performance-based design has not been adopted as as an alternative approach to cost-based design. We believe in the technology and the new technology of using performance-based design for super tall buildings, but the building officials in Dubai has not adopted the methods as an alternative for conventional design. So what we have proposed for this project is we have to do a design that meets all the requirements of the building officials and the local authorities. At the same time, we conduct a specific size study for the seismic level. This was also done by Langan International in New York. So we obtained the specific response spectra curves for the site with the accelerations. We also obtained a full, a set of ground accelerations that is suitable for the local geotechnical conditions. We will be doing a performance-based design. As now the building is under construction, so we will be having the results, in order to compare with, the conventional cost-based design. I think it's gonna be quite a large topic, and it won't be able to put everything in this presentation. Yeah.
So maybe we have another presentation on the structure of this building later. So
that would be a good idea.
Yes. So I think let's just get back to the main topic today. Thank you.
So due to the limited time, we will accommodate only 2 more questions. Okay. Another question is,
how about the solar gain?
Yes, sir. Let me check.
Last question about solar gain. So maybe I can ask.
Yes, how did you monitor the solar gain for the project? If I'm not wrong, the wider portion of the tower is parallel to the southern side with maximum heat again.
Yeah, so the tower is basically an oval-shaped flow plate. Can you hear me,
yes.
Dr. Naveed? Yeah, okay.
Yes, we can hear you.
Yeah. So it's basically an oval, and we have clad the tower in a very high-performance silver reflective glass with kind of a leading edge 21st century glass technology. And the main issue then really became the atrium in terms of solar and heat gain, because the atrium glass is uninsulated glass, whereas the rest of the tower is a very high performance glass. And we dealt with that through the environmental modeling that I showed you. Overall, this project is tremendously efficient in terms of cooling loads. It's about 20 to 25% more efficient than the existing Dubai Energy Code, which in itself is a very stringent code in terms of watts per square meter. I don't have all the detailed calculations, but we have been able to achieve our goals and exceed the code on this.
Yes, thank you. So the last question is there any reason that there is a large void at the top of the pool level, or is it just an architectural or aesthetic characteristic?
Well, I mean, when we decided that we wanted to add an observation deck at the very top of the tower, and that observation deck is open to the public, and we wanted actually to lift it roughly another 50 meters higher than the deck that you see. Can you see this rendering of the top of the tower?
Yes, we can.
Okay, great.
Yes, we can.
Yeah. And of course, if we allow the breeze to go through the tower, which is the eye of the needle, it has a tremendously positive effect in terms of the loading on the tower. So by allowing the breeze to go through these two side, almost like wing foils, the supporting structure that's holding up the observation deck, which is at the very top, are shaped almost like aeroplane wing foils, and we allow the breeze to go through. That has a very significant effect on our structural costs. Sure, and so on.
Yes, thank you. So let's conclude our talk. Thank you very much, Mr. Yahya, for sharing your valuable experience and enlighten us in the ways of thinking in design process from different dimensions, as well as ways of visualization of the ideas. I hope everyone will get knowledge from this informative talk. Thank you, everyone, and I look forward to see you in coming talks.
Thank you very much. Thank you for inviting us. We
Thank you so much.
Yeah, and my apologies for the technology failure in terms of the link. I apologize for that.
No, I think that is part of the parcel of this discussion. Please do not, I think. So it's going to be, we still have difficulty connecting a projector when we walk into the classroom every time, so not to worry.
We will solve it, but thank you very much.
Thank you so much. And thank you, Boise. Thank you so much.
Thank you so much. Thank you so much. Yeah, see you next time.
Yeah, I see a lot of friends on the list, so I hope that we will continue this discussion. And maybe we invite the structural designers, maybe Boise, to present some of his project next time. So, thank you very much.
Thank you so much. Thank you so much.
Thank you. Bye-bye.
Thank you, Mr. Yahya, once again. I think I will call you later to express our appreciation separately. Thank you.
Thank you so much. Goodbye.
Thank you so much.
Bye-bye.
Bye-bye.